Welcome to the first of two videos dealing with rates of change and differentiation. In this first video we will look at the definition of rates of change and apply it to some practical situations. In the second video we will look at the formal definition of differentiation and again apply it to some practical situations. So let's go. A rate of change is really another way of saying how one thing changes with respect to another thing. And therefore you require two quantities, two variables as we call them in mathematics. Let's look at some examples. Here are two variables, two quantities: the amount of education someone receives and their salary after they find a job. There is a connection of some sort, I would think. Perhaps the more education you receive, the more salary you will make from your job. And we can say that is a positive rate of change. Is there a connection between exercise and obesity? We would expect that the more exercise someone does, the more weight they would lose, and therefore they would be less obese. And that would be a negative rate of change because more exercise means less obesity. Now, what about when you're revising for a test? Is there a connection between the amount of revision you undergo and your final test score? You would expect that the more study you put in, the higher your final test mark will be. So we can say that is a positive rate of change. Let's see some examples of rates of change. On the left, we have a glass shape which can hold up to 10 litres of liquid. And on the right will be the graph that will show the rate of change of the volume with respect to time. So we're going to have liquid, let's say water, pouring into the glass, and we will see how the volume changes. So as the volume of the water in the glass increased, the shape we obtained is a straight line at an angle, and it looks at like an angle of 45 degrees, doesn't it? Now what does that mean? It means that the volume of the water is increasing uniformly. That means each second the same amount of water goes into the glass, which is what we expected anyway. Let's do a bit of analysis on this. The rate of change is the gradient of the straight line. Now gradient means how steep the line is, and we can get a measure of that by doing the following. We create a right angled triangle, as you can see, underneath the line, and the vertical side of the triangle is called the rise, and in this case it has a length of 5, and that's coming from the 7 minus 2 on the vertical scale. The horizontal side of the triangle is called the run, and in this case it's a length of 5, again coming from 7 minus 2 on the horizontal scale. We define the gradient then to be the rise divided by the run, and using our values it becomes 5 divided by 5, which equals 1. That means the gradient or the steepness of the line is equal to 1. And if we state that as a rate of change, the rate is 1 litre per second. That means that each second 1 litre of water is entering the container. Here's another shape we could look at. It's a cone and water will pour in from the top. Let's see how the rate of change of the volume of the water changes with respect to the height. This time the rate is not a straight line. In fact, it's a curve which we could describe as almost parabolic. So the rate of change of the volume with respect to height is non-linear. Now here's our final example, a pendulum. As it swings, it takes a certain amount of time for it to make one swing. Is there a connection between the period, the swing, and the length of the pendulum? There is, and you can see there that as the length of the pendulum increases, the time seems to be increasing as well. And the graph at the bottom left shows that. Not a linear graph, not a straight line graph. So we can conclude from this that the relationship between the time the period of the pendulum and its length produces a non-linear curve. That means the rate of change will not be constant. Look at this diagram or graph which shows the height of a person from year 1 up to year 4. Can we estimate or work out the rate of change of the height with respect to time? Bearing in mind what we said about the gradient giving us the rate of change, the first thing we can do is draw a line, the dotted blue line, starting at year 1 and going up to year 4. And to get an idea of the gradient in each section, that means from year 1 to year 2 and so on, we can draw our right angle triangles as before. There you can see that the rise for each triangle is 2 centimeters and the run is 1 year. The gradient of the line is rise over run, which equals 2 over 1, 2 centimeters over 1 year, which is a rate of 2 centimeters per year. So we can say that the rate of change of the height with respect to time is 2 centimeters per year. Notice the notation. I've got written there delta H over delta T at the bottom there. The symbol delta means a change, so that means the change in the height over the change in the time. So we have the gradient of the line is 2, which gives us a rate of change of 2 centimeters per year. Let's look at a similar situation, but this time we look at the weight of the person from year 1 up to year 4. Again, we can estimate the rate of change of the weight with respect to time by doing the same sort of things as previously. There we are, dotted blue line and the triangles rise over run. This time each triangle has a rise of 4 kilogram and a run of 1 year. So the rate of change of the weight with respect to time, and we write that as delta W over delta T, will be negative 4 kilogram over 1 year, which is negative 4 kilogram per year. Notice there's a negative or a minus. What do you think that means? If the rate is decreasing, we say the gradient is negative, and to show that we put a negative. So when we say that the rate of change is negative 4 kilogram per year, that obviously means that the person is losing 4 kilogram for each year that passes. Now there's one more combination, isn't there? The weight of the person with respect to the height. But we can do exactly the same thing. Draw our triangles, and rise over run this time will be 4 kilogram over 2 centimeters. And as before, it will be negative because the gradient of the line is negative. The rate of change is negative. That means the rate of change of the weight with respect to height, delta W over delta H, is going to be negative 2 kilogram per centimetre. That means the person is losing 2 kilogram for every centimetre of growth. Here's a practical application of what we're talking about. This time the average rate of change. Here we have a graph of the cost of 1 kilogram of tomatoes from the years 2015 up to 2018. And you can see that the value of the kilogram of tomatoes is not constant. Can we obtain an estimate of the average price from 2015 up to 2018? What we do first is, as before, draw our line, but this time starting from the first year, 2015, up to the last year, 2018. Notice that it passes through the second image of the tomato, but that doesn't matter, and it misses the third image. But we're only interested in the first year and the last year. And we make a large right angled triangle out of that line, and then we do what we have done before. We work out rise over run to obtain an estimate for the rate. So the rise is $2 because it's $3 minus $1. The run is 3 years from 2015 up to 2018, and there we are. So that gives us a rate of $2 for every 3 years, or 67 cents per year. So that means the average rate of change of the price of 1 kilogram of tomatoes is 67 cents per year. And as a final example, here's a graph Let's suppose it's the share price of some commodity over the period June 96 to June 2016. How can we work out the average rate of change from June 2004 to June 2012? We draw a right angle triangle as before. Rise over run. Rise is $24, run is 8 years. The gradient of that straight line is rise over run, which is 24 over 8. Notice the negative because the gradient is negative. Comes out to be -3. That means the rate is $3 as a drop for each year. That means each year the value of the share price is $3 less. That takes us to the end of the introduction to rates of change. In our next video, we will look at the formal derivation of rate of change by way of differentiation. See you then. Bye-bye.